This is like the professor last year when we had the rains. This room one of the downstairs rooms got flooded. The guy was giving his lecture and the water was up to here. So reminded me of that. And here's Ronald Reagan telling Frank Sinatra to stop dancing with Nancy. And Czechia. What else do we have? Salvador Dali, Coco Chanel. Selfies. Oh, Titanic. There's a lot of good Titanic photos you can find. And building the Brooklyn Bridge. So anyway, I thought since the Monday people got to see that, you get to see that too. Okay. All right. You got it. There's your microphone.
All right, guys, let's get started. I'm going to be showing you guys the tool sets that we're going to be using for labs 2 through 4. So what we're going to be doing, we're going to be using Altera Quartus and Altera Model Sim. So Quartus is what we use to see if your design is synthesizable. And what that means is that Quartus is you're going to import all your code in there, or you can code it in there, your system Verilog or Verilog, and what it's going to do, you're going to compile. And what it means by compile is that it's going to build your design and see if it's even possible to be built in an FPGA. So what that can do is from that, you'll be able to determine what your Fmax is, like what your clock frequency is, how many logic elements you used, a bunch of things. But the main important thing for this lab is to make sure that your design is synthesizable. So on Piazza, I have a post here to show you guys where to go download everything. Just click the link. It'll take you to the Altera website. So you don't want all the devices over here, so uncheck that and just check Cyclone 4. So what that is it's going to download all the libraries for all the devices. If you leave that checked, then it's going to be like 8 gigabytes of files, and you don't need all that. So what we're going to be doing is just using the Cyclone 4 device. Is that a question? So this is Windows and Linux. So no Mac, but I'm boot camping, so it works. Yeah.
So it's fine to actually search like Quartus Prime Lite Edition?
Yeah, so you want to get the Lite Edition, which is the free one.
That's
so
the free one.
Yeah. So right here, Quartus Prime Lite free, and then it includes Model Sim Altera Starter Edition, that's also free. So download those two, just check this one. Those are the ones you want.
Didn't it say something on the Reddit about like Model Sim Altera Edition? That's what this is?
Yeah, that's
okay.
Yeah, that's what that is right there.
I was searching I saw different versions of it.
Yeah, just grab those two. I mean, it's a couple of gigs, so it's going to take a little bit of space. It's very power intensive too, so I'll show you. Yeah, so get those downloaded, and then what I'm going to be showing you guys today is how to use those two tools to do Lab 2. So the first thing I recommend is just on your desktop, create a folder, because if you don't do this, it's going to go to C drive, program files, some weird directory, and you don't want it to go there. Just for simplicity's sake, just create a folder. I'm going to call this one Lab 4 Demo. It's an empty folder. So I'm going to start up Quartus. Boom. Okay, it's open. So what you want to do now is you go File, New Project Wizard, and you can hit Next. So right here, it says, what is the working directory for this project? You want to make it the folder that we just created on the desktop. So you can see that it's C Altera Lite 16. That's like where it's installed. You don't want to put your projects there. Just put it on the desktop. So Lab 4 demo. And then over here it says, what do you want to name this project? You can name it whatever you want and then set something called your top-level design entity later, so I can show you guys that, but you can type in whatever. So I'm just going to call it Lab 4 demo, same thing as my project. Hit next. We want an empty project. And then this is where you add files. So when you're coding your Verilog or System Verilog, you can use any text editor, or you can use the one that's in here, and then ModelSim also has one. So it's up to you where you want to write your code. But for the purposes of this example, I already had everything. So this is the same stuff that the professor was doing just an hour ago, the same file. So what I want to do, I'm just going to copy those files to the directory that we made our project for over here. So those are there now. And then I'm going to add those files. So it only sees my SV files, and that's fine. And for Quartus, you don't want to add your test bench. So Quartus doesn't really care about your test bench. It just cares about everything in your top level. You're not going to be doing your debug in Quartus. You're going to be doing all that stuff in ModelSim. So it can get a little weird if you add your test bench file. Just exclude it. So I added all the files. I'm going to hit next. Now, this is where it says family, device, and board settings. So if we go and look at the lab write-up, we have a device that we've given you guys. Just copy-paste that. Go back to Quartus, and then right here for name filter, that's where you want to put it. And then we see our device that we've given you guys. And you're going to hit next. So this is just saying that we're going to use simulation. For our simulation tool, we're going to use ModelSim. And the format, it depends. If you want to use Verilog, use Verilog. I'm using System Verilog, so I'm going to hit System Verilog. And then hit next again, and finish. And now it's creating my project. So the left-hand side shows you have hierarchy, which shows you, hierarchy files. So I just go to Files, and then remember I named this Lab 4 demo. So I didn't name it top level. Generally, you want to name your project or your top level the same thing. So I'm going to right-click on top level and hit Set as top level entity. So what that tells Quartus is like, hey, this is where everything lies, because you're going to be doing modules, separate modules, and then for Lab 3 and Lab 4 later on, you're going to be doing your top level, and all your modules will be in there.
Make sure they're clear on the difference between the top level for a single.
Yes, yeah. So remember you guys saw top level TB before, and I didn't add that to that project, add that to this project. So what you're going to be doing is when you're running your test for the whole thing, you're going to add all the TB files to ModelSim, and I'll show you guys an example of that. You don't want to add it here because it'll be weird. So over here in this bottom half of the window, this is what your compilation output's going to be. So you're going to see all your warnings, errors, and whatnot. So I can show you guys an example of that. I'm going to comment out one thing that was here. So if I don't comment out that line, I want to make an error show so you guys can see what it's going to do. So here we go. Green is good. Blue is not so good. Red is really bad. So you want to check to see what's happening. So you can hit this button, and that'll show you all the actual compilation errors. So if you guys use like GCC or G++, like it'll show you like things where it didn't compile for, but it might give you warnings, and warnings like you can sort of ignore sometimes. Same thing here. So you have all your like critical errors, and then you have these blue ones, which are just warnings. Warnings, for the most part, you can ignore. So if we look at some of them, we created a variable but never used it. We have a variable that's 32 bits, but we're assigning a 16-bit thing to it. So those are not so critical errors. You do want to check these time to time because sometimes there might be something that is lingering and could be causing issues. So what does a good compilation look like? So I'm going to comment that line again. Save, hit run. So if you don't have a really, really crazy computer, your computer might get really loud and sound like it's trying to put out a fire, totally normal. So what you can do for that, I can show you another trick. So most computers are multi-core these days. Everyone's got like a dual-core or a quad-core system. When you download Quartus, it's set to just use one of those cores. So what you can do is go to Assignments, Settings, Compilation Process Settings, and over here, I have it checked from beforehand. You can have it do maximum cores allowed, so I know that my computer's 4 cores, so you can set it to do 4-core compilation, so it'll be quicker. You won't have to wait like a minute or two. So near the end of the quarter, when you have your whole design, it will take like 30 to 45 seconds just to compile the whole thing and check if you just have the basic settings. So make sure you have that stuff checked. You can do it to do auto or assign it. Back to this. So over here, we don't have any errors anymore. There's no more red ones. We still have some blue ones, but they're okay for the most part. So also in the lab, so right here, this shows you what it's actually doing, what occurs in a compilation. So what it does in analysis and synthesis, that's when it's checking your system Verilog code, compiling it, seeing if we can actually make hardware with it, if there's any errors. And I'll show you guys some examples of some errors. So you could be doing something that is not allowed in system Verilog or Verilog. Then what it does in Fitter, and it says place and route. So what it does in Fitter is that for the FPGA device that we selected, that E something, whatever, Cyclone 4, you guys don't need to know the details about it. What it's doing is it's going to make your design and fit it on the actual FPGA in simulation. So it'll tell you how many logic elements you're using and registers and all that stuff. And then assembler is just it creates some machine code for its simulation. And then timing analysis, this will be important in Lab 4 where you want to find out what your frequency of your processor is. You can see all that there. And then for this class and for this lab, I think in the lab report they want you to show what Quartus produces for your module. So you're doing your ALU, you're doing your reg file, and you're doing your instruction fetch, IROM, PC. So those are the ones that you're making for this. And what Quartus does, if you have a successful compilation, it creates a netlist viewer. So a netlist viewer is like what the block diagram of that module looks like. So I'm going to open the one for this one. It's going to look really crazy. Don't get scared. See what it looks like. So it's not that bad. So if you guys are taking 141 and for those of you who have already taken it, you have like your single cycle implementation of MIPS, and it shows you like you have your instruction fetch, your control, your reg file, all the 5 stages. This is essentially the same thing that's happening here, but it's shown it in a bit more detail. So if I want to look inside what's really happening in my reg file, I can zoom in and it'll show you gate level stuff. You don't need to be concerned with too much of this because you're not doing the whole thing right now. So what you're going to do is close this. So I'm going to show you guys how you're going to use Quartus for this lab. So I'm going to close this project. So I already created one with just the ALU in it. So this was that same stuff. So you're going to code out your ALU module, and you're going to make a project. So what I recommend is you're going to make a Quartus project for each of your modules for this lab. So you can just keep it separate right now, and then when you get to lab 4, you can have just the project that ties it all together. So make 3 projects for your ALU, reg file, and your instruction ROM, PC, all that stuff. So I'm going to compile on this guy so I can show you what you guys need to make and attach to your lab report. So I'm going to go back to the netlist viewer and show you the RTL viewer. So now it's just going to show what my reg file is. This is my reg file. Before you saw it in a box, this is what you want to print for lab 2 and attach to your code and whatever else we asked for. So what it is, it's just showing you in a reg file you have a bunch of muxes, you have some gates, all that stuff. You don't need to worry about the implementation of like how to make it gate level. This is just, we want to see that the code you wrote for your module was synthesizable. So this shows that to us that like, hey, your code that you wrote can actually be made into hardware. That's pretty much it for Quartus. So Quartus does give you a text editor. You can code in here. It doesn't show you any errors until you compile. And what I'm going to do now is show you Model Sim. And that is what you're going to use to test. To start up Model Sim, I'm going to do a new project. So it's asking for a project name. I'm just going to name it the same thing, Lab 4 Demo. Project location, I'm going to use the same folder that I was using that my Quartus project was in. They could all live in the same folder. So Lab 4 Demo. So you see these other folders, DB, incremental DB, output file simulation. Those are all folders that Quartus made. You don't need to worry about what's in there. So you don't need to do anything else, just project name and select that folder, hit OK. And since I already have the system Verilog files in that folder, I'm going to add existing files. So I'm going to browse, and then I'm going to add all these files that I have. And this is where you add your test bench. So you want to include your test bench here now. Hit OK, close. So just like Quartus, you have just your output of what Model Sim is going to give you to see. You also have to compile in Model Sim. So I'm going to show you guys like the flow of if you make a change, what you have to do to test and run everything again. So the first thing you want to do, we have all these question marks. That's saying in Model Sim that this stuff needs to be compiled. So I'm going to hit compile. So you can either hit compile all or compile order. Compile all will just compile everything, just going from top to bottom, but it might give you an error saying that you have some module that you haven't compiled yet, but we're using it in a file before. So if I hit compile all, it gave me 2 errors, but if I run it again, it'll be just fine. So it ran perfectly fine this time. You can hit compile order or hit compile all twice. So what you want to do now to simulate is hit simulate and start simulation. So what this is asking me now is to choose a top-level system Verilog file. So you're always going to go to this work pull down right here and choose your top-level TB. So what you guys are going to be doing, you're going to be doing your alu.sv. I'm just giving you example file names. alu.sv and alu_tb.sv. So you would just have those 2 files in this project. And then you would select the TB. And I can show you guys an example of that after this. So I can show you again. Let me end simulation. So you're going to hit simulate, start simulation. You get this start simulation window, and you want to hit plus on work. And then you want to select the TB that you want to do your test on. So that's the purpose of Model Sim, is doing waveform analysis on a module or your whole thing. But you guys aren't going to have the whole thing ready right now. You're just going to have your module and your test bench for that module. So what I'm going to do right now is do it for the ALU example that I have, because it's not really relevant to show you guys the whole top level. It'll get really crazy looking. No. File close. I already had my ALU example created. So I'm going to add existing files. So in here I have ALU. Oh, sorry, I'm not doing ALU. I need to do reg file. New project, reg file. I'm going to create a new folder. Just call it reg file. Hit OK. OK. And then when you add existing file, I'm not sure if it copies it or if it links it, but just to be safe, I'm going to copy over my example files that I had. So if you go to TED, TritonEd, and go to lecture 4, you can see these examples. So we're not giving you guys the ones that we're showing that Professor Eldon showed you, but there's a lot of other ones on TritonEd under the lecture portion. So use those. Look at those. Those are a great resource. That's what I used last quarter to help me figure out how to code everything and use them as a template, see what my ISA was doing different. So use those, adapt those, and run tests on them. So all the stuff in lecture on TritonEd, you can go and find them there. So I was copying over reg file and reg file TB. I'm going to put that in my reg file folder. So over here, I'm going to add existing file, browse, and those two files that I just copied over. Hit open. OK. And then don't forget to compile. So compile all. So let me clear that. So sometimes you can hit right click and clear just to show you a clean output, so it works just fine. So I want to do start simulation. Let me show you guys the actual files themselves. So here's your reg file. What he does here, this is called parameterization, where you can make your reg file modular. Yeah? Oh, yeah, sorry. So this is called parameterization, where if you want to use a reg file for whatever reason for another class or another project, you can just change these numbers. So the width here means what our data path is. So we're doing 8 bits. So that's what the W is. And then depth is 4. So what that means is that we want to make it 4 bits for for your address to select a register. So what this **D means is 2 to the 4 to give you that number of registers. You don't need to do it this way, so you can totally remove this and then just hard code those values in. So address A will be 3 to 0, so we're going to have 4 bits. And then our width for our data is just going to be 7 to 0 to give us 8 bits. Same with this. And then do the same thing here. And then this we'd write 16. So I just removed his parameterization. You don't need to do it that way. You can just do it like this. I'm going to hit save. So this is how you declare a module. You have a module, and you want to give it a name. So I just called it reg file. And then you have this business with parentheses and then stuff in here. So what this is saying that this is your area of like where you're going to declare things for a module. So it's good practice to declare your inputs first to your module and then your outputs. So think of a module as like a box that's doing the job that it needs to do for a reg file. So for my inputs, since writes need to be clocked for a reg file, I definitely need a clock. I have a control signal called write, en, write enable. So I need to tell my reg file when it's okay to write. I can't just be writing all the time. Then I have my address inputs for read address A, read address B. So those can be like your two operands that you're reading from. And then I have a W address. So this is my write address. So even though I specified 3 here, in the top level, you can route like one of read A or read B to be the same as your write address. So that's that same thing of making use of the same register, but you still need to declare it all in the module's definition. Then you have 2 8-bit outputs, which is the value of the registers that you want to read. So we have 8 bits for data out A and 8 bits for data out B. So that's the definition of the module, and then this is what's actually happening in your module. So logic is the registers. So logic 70 register 16. What this is saying is that I need 16 8-bit registers. That's what that line says. And then since for reg file, you can always read out. So for when you're reading out a value from a reg file, that's not a clocked operation. So there's a distinction to be made between sequential operations and combinational operations. So when you're reading something out, that's always a combinational operation. So we're going to use assign or always com. They're the same thing. You can use either or. So I'm just going to do assign here. And it does the same thing. So what it says is data out A, which is my output for one of the registers, is equal to read address A if using read address A as long as it wasn't 0. So you can't read from address 0. So he just has that in there for another reason. So same thing with B. We just want to check to see that read address B isn't 0. Because so in MIPS and like other architectures, you have your 0 register. That's always like, it holds the value of 0. So like your G0 in Spark. So that's why he did that here. You don't need to do that at all. You can make use of your 0 register however you want. He just uses that as the hold value of 0 all the time. So now we have the sequential part of the reg file. This is where you have to rely on the positive edge of a clock when you want to write. So we have this thing called always FF, so always flip-flop at pos edge clock. So to help you understand all this stuff, I added some links on Piazza for system Verilog and Verilog. So helpful system Verilog links. So there's a bunch of websites that you guys can go to. This is a really good one, but it's an old school looking website. ASIC World. There's a bunch of other ones. And then also under resources, I have a really good cheat sheet there for you guys to use. So System Verilog cheat sheet. So this is really, really helpful. This saved me last quarter, just always referencing this. Whenever you're coding a Verilog, this will show you like the language basics. Like most CS students, they don't really like know System Verilog or Verilog off the back. I mean, not even I don't. So you always have to use some reference to see like, oh, how do I do this? Or how do I like see if the statement I'm making is correct? Or what's the syntax for a case statement, you know, or a switch case? So this is really helpful to use. And it shows you some basic stuff of like, for System Verilog to do testing and simulation, how to declare modules, blocking versus non-blocking statements, difference between registers and wires, all that stuff. So use that. So what this is, back to this, is we want to do, what this always FF at pos edge clock block means is that run this code inside here at every positive edge of the clock. So the code that I'm going to run at every positive edge of the clock is I'm going to see if write enable is high or asserted. So if write enable is 1 and my write address isn't 0, if those two pass, then I can write data in, which was one of my inputs, 8-bit input data in, to the write address register. So that's all that does. Save that. And then, So now I want to show you guys the test bench for the reg file. So let's say you've coded out your reg file. Now you need to code out your test bench. So what the test bench does is that it's going to test the reg file module that you just created. So let me remove these parameters because we're not using them. So for the reg file, for the reg file test bench, you're not going to have any inputs or anything like that. We just declare at the top, whereas before we had to like do this whole thing and had list all our inputs and outputs. You don't need to do that. So what it does here is that you want to declare your inputs and outputs to your test. So that's why I have a bit for a clock, because you just need a 0 or 1. We have reg write, which is going to be our write enable. We have our source A and source B. So those are the operands that are going to be in our instruction. So if I have 8 registers, I'm going to be given 3 bits, 3 bits. But for our example, we had it as 4 bits. And then the write value is the value that you want to give. So for the purposes of this class, everything was 8 bits. So I want to give 7 to 0. And the outputs from read A and for read B, the 2 register values that I'm reading out are also 8 bits. And then this is just like, think of reg file as like a class object, and then this is an instance of the class, of that class. So reg file is a class, this is an instance of the reg file class. So we have reg file. You don't need to do this whole parameter thing again. You can remove that. So we just have reg file, and we're going to call it UUT. So UUT is unit under test. That's just, you can call it whatever you want. Just be consistent with it. But this is like the standard of what everyone does, calls it unit under test. And now what all this stuff is. So .clk is referring back to the inputs over here. Yeah, this should be .clk, capital C. And we want to give that our clock right here. So make sure, so anything with a dot operator right there, it's just like accessing something for a class, or you just do a dot operation. So you want to make sure that the names here match the names in your module. So since I had capital CLK, I want to make sure it's the same. So what it does is, by using the parentheses here, it's saying to connect these things that I have up here, these bits, to the module that I'm going to be testing. So it's connecting this bit clock to the actual clock of my reg file module. And same thing with write enable and everything else that I have. I want to make sure I got all the names correct. Did it out, yep. So let me zoom this up a little bit. So after you declared your unit under test, that's when you actually start coding the actual test. So you always want to put your test in this thing called, so for this example, they put it in an initial begin. So what this means is that this code is always going to run after all this stuff. So it's going to run all this stuff, just declare everything. And then you're going to put your test in this initial begin block. So the initial begin block goes from here to here. So what this $100 $NS is wait 100 nanoseconds, then do this stuff, this piece of code. So what it's saying is, I'm going to check if the source, check if writing works, if I can write to a register or not. So that's what you want to do with your test bench, is check the operations that that module is doing. So for reg file, you want to test to see if you can read out correctly, if you can write correctly, if you're incrementing a register or something like that. You want to test all those things. And for your ALU, you're going to be doing a bunch of different things. So in your ALU, you might have an add instruction or a shift instruction or an AND or an XOR. So you want to test each of those cases using different numbers. So if you're doing a signed operation or unsigned operation, you want to test both those scenarios if that's what you intend to do with that instruction. So that's what it's doing here. So in between each test, we want to wait some period of time. So why we do this is that when we run it in ModelSim, it's just going to leave a little gap, and you can see what's going on. So if you smush it all together, it's going to be really hard to interpret what's going on. So put some time gap in between each test that you do. So this test right here was seeing if I can write to a register file. This test is checking that I can't write to register 0. For that example, I wasn't able to do anything with register 0. This one is saying that I can't write unless my reg write signal is asserted. So those are the 3 things it's testing. And that your last test, always put $stop. So I'll explain why that's important. So, and then at the end, you have always begin and an end. What this does is, so the other way of doing it is like clock, you can toggle it. I don't know if it works. Clock equals clock. I don't recommend doing it this way. I'm not a fan of that because sometimes it can give you errors and it doesn't let you set your time period for your simulation. So this way, this actually gives you control over what your period is for a clock. So for this, you have 10 nanoseconds asserted, 10 nanoseconds deasserted. So that means you have a 20 nanosecond period. So when you're doing a simulation in ModelSim is just like an ideal case. It's not even checking to see if your code is synthesizable. It's just assuming that your processor or your design can be made magically and run without any timing constraint. So I'm going to go back to ModelSim. I'm going to compile again because I made some changes. So it says no errors. So I'm going to go to Simulate, Start Simulation, hit the plus sign on work, select the test bench file always, hit OK, and then I get this window. So I can show you what all this is about. So on the left-hand side, you have instance and all these other things. So the instance, we created a module called the reg file TB, and then in that module, we had all these things called, we had an MNE, and we had that UUT. The UUT was the actual reg file that we're testing. So if I select UUT, I can see all the stuff that's in the UUT. So in the UUT, I had WD, I had all this stuff that I'm not really using, and I have my registers, I have my data, I have everything that I need there. So for this test, pull that up, we were testing to see if we can write to a register. We're seeing if we can write to reg1, and we should see this hex value. What's that hex? It's fine. So what you want to do is add certain parameters to your waveform window of what you want to be checking. So what I want to look at is, it's nice to have a clock. You want to see write enable. So what you do is you right-click and you hit add wave. I want to see what's in read address. Right, reg 0. Right. So I want to see what's in register 1. I want to see what's register A, register B, write address, and data in, data out B. So I've added the things that I'm going to be monitoring for this test. So if I close ModelSim right now, I'm going to lose all the stuff that I added. So what you can do is make sure that you have this window selected. So you see how it just went blue on the top bar? So make sure Wave Default is selected. Hit File, Save Format, and it's going to create a wave.do file. So this is really useful of, let's say you're testing something and you gotta go do something else. If you close it, you're gonna lose everything. So do this and it'll save this window. So I'm just gonna call it regfilewave.do. So next time when I come in ModelSim, I can open that DO file by going File, Load, I believe? Yeah, Load macro file, and it's gonna load back all that stuff. So to run this, you're gonna, so you have all these little icons. So the one that you wanna use is called Simulate, or not, sorry, not those ones. You have Break, Run All, Continue Run, Run, and Restart. So what you're gonna be using is just two of them. You just wanna use Run All and Restart. So I'm gonna hit Run All. So what it does is it opened up my code and it stopped where I had $stop. If I did not have that there, the simulation would just keep going and going and going, and you would have to close the program to make it stop. So don't forget your $stop at the end of your test bench, at the last piece of, like, at the last time period that you want to stop your test at. So I was testing this stuff, and I was testing these things, and then these things, and then at the end of the last test, you put a $stop. So I'm going to go back to my waveform. So it's really hard to see all zeros and ones, so I'm going to make it hex. So you right-click all of them, or highlight all of them, and you can make them, so you have a lot of options. You can inspect binary. You can inspect it as a decimal. You can inspect it as an unsigned value. You can inspect it as a hex or an ASCII or whatever. So for this, I'm just going to do it as a hex. And then you have zoom full. What that does is it's just going to like auto range everything for you. So if I hit that, it auto ranged everything for me perfectly. So remember at the beginning of the code we had $100 ns, and that means to wait 100 nanoseconds. So that's what happened here. I waited 100 nanoseconds and nothing happened. Then the first test was seeing if we can write this value. So this is actually too much. We should just be writing half of this. Let me see. Yeah, because it's only 8 bits. So the way you want to do this, inspect to see if things are working correctly. So at the first test, at the start of 100 nanoseconds, I was enabling write address. So not enabling, but I was giving it a value of 0, 1 in hex, which means register 1. And then I was giving it a data in of this hex value right here. And what else was I doing? I was giving a write enable. So if you see write enable, it got asserted at 100 nanoseconds. So what that's saying is to write the value of data in to register 1. So you see that happen at the start of the next clock cycle. You won't see it happen immediately. It's always going to wait for the next positive edge of the clock, and you'll see it there. So that's why we see 6, 7, 8, 9, A, B, C, D in register 1. So if I want, I can look at all the registers. So if we go back to this and I right-click, add wave, I can see all the registers here. But it's showing all X's because I need to run the simulation again. So to run the simulation again, you want to hit restart. So hit restart. You're going to get all this stuff, leave them all checked, hit OK, and then hit run all. It's going to stop at my $stop, go back to wave, and now you can see everything that's in the registers. But default, it's as a binary, so I'm just going to make it a hex. So these two, this one and this one are showing the same thing. But you can see everything else is unaffected. So that's what ModelSim does, is you want to run tests for everything. If your reg file, for your program counter, for your ALU. So for your instruction ROM program counter, you want to see if you're incrementing the program counter correctly, depending on the flags you're giving, to see if you're branching correctly, see if the program counter changes up or down, if you're branching backwards or forwards. So you want to test all those things. Yeah, that's pretty much it, guys. Do you guys have any questions on Model Sim Recordis? It's a little overwhelming at first, so what I recommend is download it and just jump in. That's the only way you're going to learn how to do this stuff is just hit all the buttons, make it crash, restart it, run it again. That's the best way. Yep, that's it. Oh yeah, look at those links too that I put on Piazza. That's super helpful, especially if you haven't taken 140L in a while.